No, it didn't. So this might seem like a silly question, but when I was a kid, I had this question before curiosity was beaten out of me, right? No. Kids are curious. I was curious. You know, I know that if I grab my Yeti here and I lift up, I move it up. So I used to wonder, if I grab my shirt, lift up, why don't I come off the ground? Why don't I come off the ground? Right? Answer it. Can someone answer that question? Gravity. You're not explaining anything. You're just saying a word.
And your shoulder is connected to your body, so you're lifting your elbow up.
So what does the fact that your shoulder is connected to your body have to do with anything? You're on the right track. Yeah. This isn't. It's an easy question that has an easy answer. But if we want to be specific and provide a physics answer, then we need to actually be a little more careful. Okay. By the end of this period, you will know why I can't lift myself up. Okay. If I was standing on a perfectly frictionless surface, okay, meaning like ice, but even slipperier than ice, more slipperier than ice, and I was about to square off with Colin. We're about to throw down. Colin, Connor, same thing. And Colin punches me in the face. Connor punches me in the face. I'm going to slide backwards, right? If I don't fall over, if I just take it, he's going to hit me and I'm going to start sliding backwards, right? If I hit myself in the face, am I going to slide backwards?
Probably not.
No, I will not. My head will move backwards, but my body will not. Okay. Why? Same reason. Same reason that I can't lift myself up off the ground. Okay. That's what we're going to answer by the end of the day by analyzing pretty much the same thing that we've been talking about for 2 days now. Okay. This will be the end of this. And if you understand everything, first of all, you'll be able to understand how to apply Newton's first and second laws to complex situations in addition to simple situations. And then you'll understand how to know whether Newton's first law or Newton's second law will apply. And then you'll also have some intuition that if you follow along and you really understand, you'll know more about physics than the vast majority of people who will even have taken physics classes in their lives. Right? So we're still going to go from the same situation. And originally I had planned to actually do this demonstration and have it set up, and I did have it set up, but we just didn't get there for second period. So when we come back, the Monday we come back, we'll address the same situation, but not theoretically on the board, in reality with the setup right here. Anyway, so I got mass 2, mass 1, and angle of elevation theta. All right. And we calculated a specific value for M1 that put this system in stable equilibrium, correct? Any other value for M1, like theoretically, any other value, 1 additional gram, 1 less gram. And this system does what? Accelerates. The bigger the difference between, the bigger the mass I remove or add, probably the bigger the acceleration I would expect, right? So really there's only one specific value for M1 that will put this system in stable equilibrium, static equilibrium. All other values for M1 will cause the system to accelerate, okay? And that's the difference between Newton's first law and Newton's second law. Newton's first law in FL applies when what condition is true about concerning the total net force? Zero. Net force 0. I could have phrased that better. I'm sorry. But my brain is fuzzy and I need a lot of sleep. And I haven't had enough. So, yes, Newton's first law applies when the net force, sigma F, is just equal to 0. If you know the net force on a system or an object, what do I mean by system? Well, it could be a system of 2 objects like I have here. It could be a system of trillions of objects like our solar system. If the net force on the system of objects or the single object that we're dealing with, if it's only one object, if the net force is 0, Newton's first law applies, and an object at rest will remain at rest, an object in motion will remain in motion at constant velocity in a straight line. If the net force is not 0, then we say we're dealing with Newton's second law. Newton's second law says that the net force, first of all, it's not 0, but it does equal something else. Did anyone read that or see it from the videos or remember it or anything?
Net force.
Equals what?
Net force or
It's alright if you don't remember.
mass times acceleration.
Mass times acceleration.
I remember because I literally learned this.
Probably in engineering. Yeah. So if you don't, if the videos didn't go over that, that's fine. Don't worry about it. So a brief aside here: the net force is equal to mass times acceleration. This is Newton's second law in math form. It is a vector equation. The net force is a vector. The acceleration is a vector. Is mass a vector? No. If we have a vector equation, which, by the way, all of our kinematic equations are, and this guy is. If it's a vector equation, not only is it telling you that the magnitude of the values on this side, meaning the numerical value here, must equal the numerical value here, what else is it telling you if it's a vector equation? The directions have to be the same, right? So whatever direction the net force points is the direction that the acceleration is. That should make sense, right? I pushed my Yeti towards Connor. I push it towards Colin.
It goes towards Colin.
And it accelerates towards Colin. Right, Colin?
Yep.
Right. I'm going to start calling you not Colin now. You know Evan? Evan Pickett?
Yeah, we know Evan.
I called him Ethan a couple times because it's like Connor and Colin. So now we call him not Ethan.
I saw him have a birthday.
Okay. Now, where does this come from? First of all, we will prove this. We will experimentally determine this law. This is a law. This is Newton's second law of motion, expressed mathematically. How do we arrive at this? Well, we can talk about it by talking about proportions, proportionalities. Okay. There is a symbol that means and this is gonna be big for, again, true understanding, like deep understanding. This is one of the places where it starts. So there is a mass symbol. Is proportional to. Obviously, is equal to. What's the symbol for that? Equals. Or is the same, or is or was equals. Right? Of multiplies. Per divide. Is proportional to. Does anyone know what that symbol is? No, 3 lines. That is defined as. I think Connor has it. What is it? It's like an infinity, but with 3/4 of an infinity. It's kind of like alpha, the Greek letter alpha, but it's kind of more like this, whereas is proportional to is kind of more like that as opposed to that. And it doesn't matter. All I'm saying is that this is how we can say things are directly proportional, right? So if I said y is directly proportional to x, I might not know what the graph looks like, but I know it's what? It's what? Which means it's linear and it goes through the origin, right? Yeah, we know it's linear, right? If y is inversely proportional to x, I would say it looks like this, right? As x gets bigger, what happens to y? It gets smaller. They're inversely proportional. What does that graph look like? Right. We see these in physics a lot. Usually we're just interested in here, first quadrant, because that's where the values are positive. So that's how you'd say y is inversely proportional to x. Well, it can be experimentally determined, and you'll do this so you can convince yourself of this, and not just based off of what I say. You can experimentally determine that the acceleration of an object is directly, and I'm just going to talk about the magnitude. The acceleration of the object is directly proportional to the amount of force, the net force. Guess what that means? If you push something harder, it's going to accelerate faster. Okay? Pretty complicated.
I don't understand.
But this does tell us that there's a linear or proportional relationship between the acceleration and the force. And I also know that the acceleration is inversely proportional to the mass. Make that make sense in your head. As I increase the mass, if I give the same push, if I push on several objects with the same force, the objects with the biggest mass are going to have what? This biggest or smallest acceleration? the smallest, right? If I try to push the remote here, real easy. If I try to push my car and put my car in neutral and try to push my car with that same force, theoretically I'll get it to move, but the acceleration is going to be real, real tiny. Okay? So they're inversely proportional. And it turns out that when I tie these proportions, and this is how science is often done, you make observations in nature and you recognize that as this one thing changes, this other thing changes in response. Sometimes it changes proportional, inversely proportional. Inversely proportional to the square of something. Like, there's all different types of proportions. So you recognize those proportions and then you tie them all together into an equation or a law. Okay? In this case, we tie them together into Newton's second law. The acceleration is directly proportional to the force when we put the net force in the numerator. Inversely proportional to the mass, we put the mass in the denominator. It's a vector equation, so put the vector symbols over the acceleration, net force point in the same direction. So just by considering the proportions, I get the law, and I hope we can all agree that this is the same thing as that. This is how we think of it when we're experimentally determining it. We'll do that in the lab the week we come back. This is more applicable to actually solving problems. Okay, just writing it this way. All right. Now I'm going to do an aside here to talk about some chemistry stuff that you learned last year. If you were doing what your chemistry teacher asked you to do last year. And so I'm going to talk about this process, but it's not always this simple. It's not always as simple as recognizing some proportions and then writing an equation directly from that. Sometimes it's not that simple. There's a case where that's not that simple. Let's talk about your car tires. Okay. This is a good time to talk about it, by the way, if I haven't said it already. It's about to get colder. What do you need to do? You need to pump air into your tires when it gets colder. Why? Lose pressure when the temperature goes down. So as the temperature goes down, the pressure goes down. So what would I say about the proportional relationship between pressure and temperature? They're directly proportional, right? If one goes up, the other goes up. One goes down, the other goes down. Can we be sure that it's not directly proportional to the square? So no, we can't be sure of that without experimentally doing some science. Scientists have done this. They've done it since the, I think, 1800s, maybe even 1700s. They've done it. They know that the pressure varies linearly or proportionally with the temperature. Okay? The pressure of a gas and the temperature of that gas are directly proportional. So what happens to the pressure then when I start filling up my tire? It goes up. What am I doing? What am I changing when I'm pumping pumping air into my tire? What am I putting in the tire? What am I physically putting in the air? How do I quantify how much air I put in? The number of moles of the gas molecules. Right? So if I add more moles of gas, it should make sense that the pressure is going to go up. And it turns out that that is a direct relationship as well, direct proportional relationship as well. As you increase the number of moles of gas in a container, as long as you don't allow that container's volume to change, the pressure obviously goes up, right? You should know that. When you try to pump air into something that already has air in it, it's hard, right? Okay, because the pressure goes up. All right. Volume. Let's say I take a balloon. Let's say I take a container and I put gas in it, and then I compress the container. I make the container smaller. Like, this is what happens in your car engine, right? We'll talk about the physics of this when we study energy. Why does your car work? Because it has an engine. The engine is an engine block. It's just a giant chunk of iron that's very precision cut. So you have these cylinders, right? When you're talking about cylinders, those are cylinders cut into literal cylinders, shaped like this, right? Cut into that iron engine block. And then we put pistons in those cylinders, right? That are attached to things that do rotating stuff. And they move up and down. The pistons move up and down. That linear motion, linear energy is then converted to rotational energy through the drivetrain and the crankshaft, and then that gets your tires spinning, and that's what gets your car going. Okay. But what happens, and this is in a normal car, you have something called a fuel injector, which does what? It injects fuel into the cylinders, into the chamber that is cut off from the outside. Right? There's seals in here. When those seals bust, by the way, that's when your engine breaks down and you got to have it rebuilt and stuff like that. But anyway, so gas gets put in there by the fuel injectors that inject the fuel. And then what do you do with the gas that's in there? And by gas, I don't mean the liquid gas that you pumped in your car. At this point, it's vapor, right? Gas has a very high vapor pressure, so it very readily evaporates into gas. And it's in gaseous gas form when it goes in here. Then it gets ignited by what? Does anyone know?
Spark plug.
The spark plugs. That's what spark plugs are for. The spark plugs make a little spark in there, which causes an explosion, right? And that explosion creates higher pressure than it was before, which pushes the piston up. And then the exhaust goes out through the four-stroke process, and then the piston goes back down, and it just goes on and on. The more cylinders you have, the more faster your car goes, right? Unless you're talking about turbos and all that kind of crazy stuff. So most cars have 4 or 6. We got a fast car like your favorite teacher. It might have 8. If your last name is Evans and your dad teaches at the school, you might have a 3-cylinder car. I should have put that in the video. Huh? I only say that because we were talking about it last period. What?
3 cylinders is a Toyota RAV, like one of the older ones.
Huh?
No, you whipping that.
Toyota RAV. I just got a new car.
A RAV4?
Yeah.
It's probably a 4-cylinder. Hey, I had a 3-cylinder car at one point. You ever seen a Geo Metro?
A whopping 78.
I had a Geo Metro. Look up Geo. You don't see them on the road anymore because they don't last more than like a few years. That car literally fell apart. And it had 3 cylinders and it could barely make it up the hill. But I was poor at the time and that's what I could afford. Okay, turns out though if you drive a diesel engine, you don't never put diesel fuel in your car engine if it doesn't have a diesel engine because it will ruin it. It's not going to run. Diesels don't have fuel injectors. What do diesel engines do to cause that gas to ignite? The thing just compresses the crap out of it. Okay? Compresses the crap out of it. This guy pushes down real fast using the battery power to kick it off, but once it's going, then it's just going. It compresses that. You make that volume much smaller real fast, right? The pressure, what happens to the pressure? The pressure increases, right? But if you do that fast enough, the temperature will also increase, right? You compress it, you make the volume smaller, you make the pressure bigger, you make the temperature bigger. You do that fast enough, the temperature gets high enough to ignite the diesel fuel in the chamber, which then will cause the piston to start moving, which helps it as one goes up, another one's moving down, right? They work together like that. And so that one that's moving down is now going to compress the gas to the ignition temperature, and then that happens, and it's just a cycle. So what happens there, the proportionality we were talking about there, is that the pressure increased when I decreased the volume, right? So the pressure is not proportional to the volume, it is inversely proportional to the volume. Okay. Now I took 2 proportionalities and wrote Newton's second law of motion with them. I can take these proportionalities and try to write an equation. All right, well, P, temperature is the numerator, directly proportional, number of moles, numerator, volume. Okay. If I did this the way that I did the Newton's second law thing, this is the equation I would get. Is that a valid equation to those in the know? No. Let me write another way. What if I multiply both sides by V? Wait. What am I missing? An R. What is R?
Constant.
The ideal gas constant, otherwise known as a proportionality constant. Sometimes, more often than not actually, when we go look out in the nature and we notice these relationships, we can combine them into an equation, but that equation needs to be modified by a proportionality constant. Okay. Why am I pointing this out? So you understand the process, and you understand that in Newton's second law, it's not needed. A proportionality constant is not needed. Okay, so it's just net force equals ma. Another case, Newton figured this out. Newton figured out that the force of gravity between two astronomical objects is directly proportional to the products of their masses. So if I want to know the force on the Earth from the sun, that force is going to be proportional to the product of the mass of the Earth and the mass of the sun. The force of gravity between them will also be inversely proportional to the distance, not the distance, but the distance between them squared. Okay? But the proportionality constant that ties these together into an actual physical law that describes reality is big G, not little g, big G. That's the universal gravitational constant. With that, I get Newton's law of universal gravitation. Right? The proportionalities don't actually work until I include that proportionality constant. Okay. Those are typically experimentally determined. There are some that you can derive from first principle, like the fine structure constant. It's a pretty interesting one. You can derive that just by, I'm not going to get into it. But these other ones, like R here, experimentally determined. Okay? What's cool about this is that you take any gas that behaves like an ideal gas, which is almost all of them. You multiply its pressure times its volume, no matter what it happens to be, no matter what either of those happens to be. You divide that by the number of moles present in that volume at that pressure. Divide that by the temperature of that gas that exists in that number of moles in that volume at that pressure. And what does that number, what does that always give you? That gives you the ideal gas constant. So they've known this for a long time because we've been able to make these measurements of a gas for a long time. And so we've known this. And every time no matter what, you change one of these, then the other ones are going to change such that that calculation always gives you the ideal gas constant. If in the case of Newton's second law, you're trying to do this to find the proportionality constant, it comes up being what? Can you tell me? 1. If that's 1, then no proportionality constant is needed. In the case of the ideal gas law, that's not true. In the case of Newton's second law, it is true. No proportionality constant is needed. One of my jobs, I consider it to be not just to give you the laws, have you memorize them and use them to solve problems. I want you to understand where they come from. Maybe not at the base theoretical level, but understand what the people that came up with this stuff. It's not like just made it up out of thin air, right? There's a lot of work that went into it. Sometimes theoretical, sometimes experimental. But it's not, they didn't just pull this out of nowhere, okay? I know that's what you're thinking, Taylor. You need to stop.
You're right.
Okay, good. I'm glad you agree. All right. That was our introduction to Newton's second law, having to do with two laws that weren't Newton's second law. But now that we understand where that comes from, we can now analyze the situation. Let's assume that I'm going to overload M1. I'm going to put more mass on than what's required to maintain a state of static equilibrium. If I put more mass on M1, which way does M1 accelerate? Down. If I know a system's going to accelerate, I like defining my coordinate axes so that they point in that direction. Okay? If I call down the positive direction for M1, then any acceleration I calculate will be positive, and I'll kind of mitigate the hassle with negatives if I do that. But Mr. Graham, up is the positive direction. No. No. Coordinate systems are what? Starts with an A? Arbitrary, which means up to your prerogative, right? You could call up the positive direction here, but when you calculate the acceleration, what's going to be in front of that number? A negative sign. Okay? So I'm just going to call down the positive direction because that makes it easier for my brain to handle. And then I remember what I talked about yesterday, where you can think of that pulley as redirecting your coordinate axes so that the downward motion of M1 corresponds with the upward motion of M2. Up the ramp motion of M2, I should say. Right? So I'm going to call that, specifically I'm going to call out the positive x direction here because I know I got to deal with both directions for M2. Okay? All right, so I've drawn a diagram. I've kind of established my coordinate axes. I'm going to do M1, handle M1 real fast here. What do I mean by handle it? I'm going to draw a free body diagram, then write an equation using Newton's laws. Okay? What forces are acting on M1? Tension and gravity. Gravitational force, M1G. By the way, that equation I showed you, Newton's law of universal gravitation, it is by analysis of that equation that tells us why your weight is calculated M1G. This isn't random. They didn't just make this up. It comes from more fundamental principles. Okay? And we'll go over that, just not quite yet. And the tension force. Is the tension force larger in magnitude or smaller in magnitude or equal in magnitude to the weight force? You okay? Is the tension... Yesterday, the tension was the same, right? Yesterday, this is my free body diagram. They're the same. Because the object wasn't doing what? Accelerating. So they have to be the same because the net force has to be... Net force has to be? Net force has to be? These two have to be the same size because M1 we want it to be at rest, right? Therefore, the net force had to be 0. Everyone should be saying 0. If you're not saying 0, you have a misunderstanding of like the fundamentals behind what we're doing here. So now we know that we're accelerating downward. M1 is accelerating downward. Are the two forces still the same size? No. I told you, this is a vector equation. Whatever direction the acceleration points, the net force better be pointing in that same direction. Which way is M1 accelerating? Which way? No, it's accelerating down. Which way does the net force have to point? Down. Which means which force here has to have the larger magnitude? Gravity. Yeah. Don't make it more complicated than that. I know M1's going to accelerate down. Newton's second law says that acceleration, that net force are in the same direction. So I know that the upward force that's fighting M1G, the tension force, has to be small. Right. You want M1G to accelerate even faster? Cut the string. Cut that force out. Now the net force is larger because none of the weight force is being offset by tension, and so it falls faster. All right. Free body diagram. Then I do what I did yesterday. I say the net force on mass 1. But now, because I know it's accelerating, the net force is not 0. And anytime it's not 0, it's going to be equal to the mass times that mass's acceleration. All right? And when I unpack sigma F1 here, considering my coordinate system that I have defined, what do I replace sigma F1 with? M1G, positive or negative? Positive. Positive, because it's pointing down, and I've defined down as the positive direction. You guys remember, don't make this more complicated than it needs to be. This, look at your free body diagram, list the forces. That's the net force is the vector sum. All right, well, they're vectors, so they can be positive or negative. M1G is positive because I've defined that as the positive direction. Tension is negative because I've defined up as the negative direction. So M1G minus T is the net force. But that doesn't equal 0 here. That equals M1 times the acceleration. Okay? And look, in a manner almost identical to what I did yesterday when the net force was 0, I have generated an equation. Okay? Involving the forces on an object, the object's mass, and that object's resulting acceleration. By the way, if I can use Newton's second law to calculate an acceleration, which I can then use that acceleration if I know, say, some initial conditions like where the object started or how fast it was moving when it started and in what direction. If I know that acceleration, I can fully describe the subsequent motion of that object as long as it maintains that same acceleration. Right? For similar considerations, that's why when we send spacecraft out to the outer reaches of the solar system, like the Voyager spacecraft or the Pioneer spacecraft or the New Horizons spacecraft, they've all, we launch them on rockets that are gigantic, rockets that are, I can't draw a rocket, rockets that big, to deploy something that will go to the edge of the solar system and beyond, millions of years from now. Those things are still going to be moving. They're still going to be flying through the solar system, through the galaxy. But the thing that's flying through the galaxy is about that big, and it's inside of the module at the top of the rocket. What is in all of this? What fills this? What fills it? Fuel. That's all fuel. That's all fuel. By the time it gets to space, it's in a little tiny module. More than 90% of the mass that started at the ground is not there, and that's like 100 miles up. That's barely off the surface of the Earth in the grand scheme of things. Right? 100 miles versus these things have traveled billions of miles at this point. Okay? All of their fuel, in essence, is gone once they're a couple hundred miles away from the Earth. We know, though, that when they're at that location, once the fuel's pretty much gone, we know what direction it's moving and how fast it's moving. We know its acceleration based on where it will be in the solar system at that time, its distance from the sun, which dominates. But then also once it starts getting close to Jupiter, which the Voyager spacecraft did, Voyager 1 did, then that gravity is going to be hit. So it's a lot more complicated when we're talking, but it's the same basic principles. It's the same basic principles. If we know the force is acting on an object, even if it's a satellite, a space probe flying through the solar system, if we know about the forces and we know the mass of the object, we can determine its acceleration. If we know information about its motion at the beginning and that resulting acceleration, we can describe all further motions of the object. Which is why when we set those things going, they're coasting, right? The New Horizons took over 10 years to get to Pluto. Traveled almost 4 billion miles, I think, at this point. And for the vast majority of that time, it's just coasting. It's just chilling, right? We can't put enough fuel into something in space that would be able to burn for 10 years. No way, not a chance. So we just make sure that it's going in the right direction when it starts, and then it just coasts. Okay. Now, is it always perfect? No, right? That's one of the things I also like to make sure I instill in my AP physics students. No, they still have to keep a little bit of fuel on those for little corrections, right? Because nothing is perfect, and so our models aren't perfect. The computer simulations won't be exactly perfect. So yeah, we have to correct for that. But the amount of fuel that they save for those purposes is like less than a fraction of 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 1% of the fuel amount that they start with. Okay? It's barely anything in relation. Okay. That was a small aside. Let's get back to, again, that's big picture. That's NASA stuff, right? That's NASA science stuff, NASA engineer stuff. But this is where it starts, by analyzing this type of motion, right? And the forces that govern this type of motion. All right, so I got one equation. First, how many equations do you think I can generate here?
60.
Nope, wrong. Using Newton's laws. How many did we get yesterday? 3. One for each axis of motion. One for each axis on each object. There's only one axis on M1 that's interesting, that has anything that we need to consider. But there's 2 for M2. So we can get 3 equations here. Just like, again, the approach is almost the same. The only difference is the right side of the equation. It goes from being 0 to being MA. Right? That's the only difference. So for M2, let's do M2's free body diagram. What forces are acting on M2?
Force of gravity.
Force of gravity, M2G. Let me draw the one that we had yesterday, okay? Because I don't know if you noticed, but I was pretty deliberate when I was drawing this with how large my vectors were. Because when I've decomposed this vector, the mg, the one that I had to, I drew these such that when I decompose them, if the net force was 0, this guy should be the same size as that guy, right? Just like if this guy wasn't accelerating, this guy should be the same size as that guy. So I drew it so that this guy would be about that big, and this guy would be about that big. When I overload M1 to cause M1 to accelerate downward, M2 accelerates up the ramp. What about this free body diagram changed? Which force changed? The tension force changed, right? If you have something on a string and you start hanging weights off of it, doesn't it put more tension in the string? Even if the thing starts accelerating down, it's still going to be more tension in the string. Right? If I start pulling down on this guy's going to break eventually. Right? So yeah, the tension had to go up. The tension went up over here, and since this tension is the same as that tension because we're assuming an ideal pulley, then this tension had to go bigger. And so I would draw that bigger Pretend that tension and that tension are the same size. But now that I see, this guy is larger than that guy, so this guy's going to overpower and we're going to accelerate up this way. Okay. Remember our directions here, right, are up the ramp we defined today as the positive direction. So up this way is the positive x direction. This is the positive y direction. All right. Let me just decompose this guy real quick. Remember that this angle here is always the same as the angle of elevation of the ramp. Since you guys love geometry proofs so much, you can prove that to yourself. This guy is the opposite component, so that's n2g sine theta. This guy is the adjacent component, so that's n2g cosine theta. All right. Consider the y direction. Does Newton's first law or Newton's second law apply to the y direction on M2?
First law.
Newton's first law. Because we don't see what in the y direction?
Net force.
We don't see a net force, and we would know that we don't see a net force because we don't see acceleration, right? If the net force in the y direction was not 0, then it would be either accelerating this way or accelerating this way. That's not happening, right? And you're like, well, that direction is arbitrary. You just picked any direction. You pick any direction. Pick a direction here. It goes through this line here. I'm not going to draw it because I'd have to erase it. The net force in that direction will be 0. What are you going to have to do, though? You're going to have to find the component of the normal force in that direction, the component of the tension force in that direction, offset by the component of the weight force in that direction. That's going to be a nightmare. That's going to be gross. I wouldn't even attempt it. But if you did, I guarantee you that the net force in that direction would be 0 if the system was at rest. Okay. This actually isn't a case of that because, yes, while the net force in the y direction is 0, is the net force in the x direction 0? No. If it was, then M2 wouldn't be accelerating up the ramp, which would logically imply that M2 wouldn't be accelerating down. Okay. If M1's moving down, M2 is moving up the ramp. Otherwise, that would imply that the string broke or something. Right? Okay.
Moving up the rankings.
What's that?
It's moving up the rankings.
Yes. So let's talk about the y direction motion here. We know that Newton's second law applies, or Newton's first law applies for the y direction. So if I'm looking for the y direction on M2, I can go straight to what equation? Blank equals blank. Again, this make it easier on yourself. Draw the free body diagram, use it to help you write your equations. N equals n2g cosine theta. I said this yesterday several times. I'll say it again. I'll say it several times before the end of the year, especially the end of this unit. Some students just fight me on drawing free body diagrams. They want to draw them with lines instead of arrows. They don't label them. There's no point. You might as well just not do a free body diagram if you're going to do that. You're not going to get points for it on an FRQ. You need to draw them with arrows. You need to understand what they mean. And you need to understand that you can literally go directly from this diagram to the equations. Okay? If you're making it more complicated than that, you're doing that to yourself. And you're making this harder than it needs to be. Yes, physics isn't easy. This stuff, if you do what I'm telling you, and you do what the notes that I gave you tell you to do, it makes it as easy as it can be. I guarantee you that. So that's another equation. That's easy to get. But we can't, let's say the problem here is calculate the acceleration, and we can measure the following. We can measure these values. Let's say we can measure the two masses and the angle theta, and we always know g. With that information, if I knew this, could I calculate the acceleration of the system? Okay. If these are my known values, what are my unknowns here? Again, this is another thing. Make it easy. Guys. The rule is, how many unknowns do you have? You need that many equations to solve for them. So when I ask you, these are my known values, these are my two equations, can I solve for the acceleration? All right, well, how many unknowns do I have here? 2. The tension and the acceleration. How many unknowns do I have here? Technically 1. I can calculate it real quick.
Yeah.
But does knowing the normal force or any of this help me with this equation here?
No.
No, it doesn't help me deal with the tension. That's the problem here. I need to know the tension in order to calculate the acceleration. So I let the math tell me that I'm not done yet. I need another equation. I don't have enough information now. But since I know, I haven't exhausted the possibilities yet. I can look at M2 in the x direction. In the x direction, are we accelerating or are we not accelerating?
Accelerating.
You're accelerating. Does that mean Newton's?
Number 2.
Does that mean? Yes. Does that mean Newton's first law or Newton's second law is at play here? Newton's second law. Net force on mass 2 equals mass times acceleration. Right? Right?
Yeah.
Right. And then we unpack sigma F2. How many forces do we have in the x direction? 2. Which one's positive? Tension. Remember, our coordinate system defines that as the positive direction. So I have a positive tension and a minus n2g sine theta. That equals mass times acceleration.
Should it be M2?
Yeah. Oh, yeah. Oh, M2. I was checking seats, paying attention. Good job. Everyone else gets an F for today. Oh, you just lost it because you said let's go.
Let's go.
Yay!
Okay. So now we have another equation. Now do we have enough information to solve for A? Yeah,
Well,
we do.
yeah. We just gotta rearrange.
I got these two equations only have 2 unknowns in them. If I just consider the system of those two equations. How would you guys go about solving this though? That's my question.
Get T alone on both questions.
Get T alone on both sides. So T, I just add n2g sine theta to both sides. So T is going to equal m2a times plus. Like I got to add this guy, m2g sine theta. And for this guy, I think of this as adding the tension to both sides and then subtracting m1a from both sides. You cool with that? So in which case, I end up with, do as many steps as you want, but you'll end up with T equals m1g minus m1a. So these are the two equations that I can use to actually solve for A. Right? Because if T equals this quantity, and T also equals this quantity, then this quantity equals that quantity. And I can just set those equal to each other, and I'll do that up here. So I have the first equation is m1g minus m1a. The right side of the second equation, which is the same thing.
M1g minus M1g.
Sorry. Right? And that equals m2a plus m2g sine theta. All right. This is where some students get a little confused, especially if you're in Algebra 2. How can I solve this for A? First of all, if you're kind of unsure, what is making you feel uneasy? What's it? There's an A in different spots, right? How do I take care of that? Add M1A to both sides. And do what? Yeah, I'm going to add M1A from to both sides. And I'm going to subtract M2G sine theta from both sides. If you don't see Y, you'll see Y in a second. So on this side, M1A goes away. On this side, M2G sine theta goes away. So the left side now is M1G minus M2G sine theta equals M2A plus M1A. Are we out of here at 154?
Yes.
Why does it take so much longer with you guys? All right. So we're not going to get to the take-home point, unfortunately, so we'll start when we come back. So don't forget any of this, please. We're not done yet, though. How do I solve that for A? Yeah. Yeah, factor out the A. M1G minus M2G sine theta equals A times M2 plus M1. And then how do I calculate the acceleration there? Divide both sides by M2 plus M1. If you're like me, you'll put in parentheses before you cross it out, because, you know. Is M1 plus M2 the same as M2 plus M1? Yes. And so look, our equation is the acceleration is the weight force of M1 minus the component of M2's weight force pointing down the ramp divided by the total mass in the system. So that's how we could calculate the acceleration there. I did have one student second period ask, is that always the equation for this when I see this? And my answer to that is kind of, but don't memorize that. You need to know how to get there, right? That's knowing the physics. Memorizing when I have a frictionless ramp with an ideal pulley and two masses hanging over and the system is accelerating, I get this specific equation for the acceleration. Memorizing that is not knowing the physics. Memorizing that is just memorizing something, right? So you need to know the process of getting there is knowing the physics as an AP Physics student. That should be your goal.
Just because you can
And we will start when we come back directly from here and answering the question, if Taylor Lee punches himself in the face, why doesn't he move? Yes, his head might move, but his body ain't going to move. I can guarantee you that. And then we'll have him demonstrate that with various forces. All right.
Guys, it doesn't work.
like you can't pull on the straight.
Oh, subscribe. What do we say? Smash that like button. Smack the like button. Join me on my MySpace page.
Donate to my GoFundMe.
Donate